Hey, this is Eli Kilgore, and this is my Physics 2211 lab on projectile motion. Here's a quick introduction to the lab. In this experiment, we threw a ball in 2D and measured the X and Y components of this ball over time. The main forces acting upon this ball are the force of drag and the force of gravity. We used the tracker application to collect data of this ball as it traveled in the X and Y directions. Then we made computational models in GlowScript of the code with and without drag, of the ball with and without drag. The main principles used in this lab are momentum and Newton's second law. We use the equation that net force is equal to the change in momentum over the change in time. And then we used constant acceleration due to gravity using the gravity as g equals negative 9.81 meters per second squared. This constant acceleration was used in the computational model where we did not account for drag. We also used the force is equal to mass times acceleration, and the force of drag is equal to negative bv squared, with this b being a constant for drag that we solved for. Here on the screenshot, you can see what the tracker model looks like. The system was the ball, and the surroundings were the drag and gravity that acted upon the ball. You can see in the application that the tracker has a graph and a table that accurately predict the motion of the ball over time. Here is my GlowScript code. One on the left that does not have drag, and the one on the right which does have drag. So in the one on the left, you can see that the net force vector is equal to negative 9.8 times 0.005 being the mass for the ball, which we calculated. This net force vector only has gravity acting upon it. And on the right, you can see the net force vector is different and also counts for the force of drag. This graph here shown represents the three models that we use to represent our experiment. The yellow model is the computational model with drag. The red model is the computational model without drag. And the blue is the observed model shown in GlowScript. Some experimental error that we need to be aware of in this experiment are, first, the tracker software may not be entirely accurate. We may have calculated the mass wrong. There could be some human error in the calculations or the predictions that could greatly change our outcome. And then the drag could be off in this experiment due to it being such a short fall. So none of the three models I used actually predicted terminal velocity, and I think this is due to a minimal time spent falling by the ball because it didn't have a long enough time falling for it to reach its terminal velocity. And in the future, one way to fix this would be by using an experiment with a much higher displacement in the Y component, such as dropping the same ball from the top of a very high building, giving it more time to reach its terminal velocity, which we could then calculate. If the object were thrown straight up with the same initial speed, it would take longer to reach the ground. This is because the object was originally thrown at an angle, and with this angle, that means the Y component is smaller than the actual velocity at the angle. And if the velocity was thrown straight up, it would have a greater Y component because the angle would be 90 degrees and it would only be moving in the Y direction. So with a greater velocity, that means that there's greater time using the formula V equals AT with a constant gravity. Thank you for watching.